Hello, we're students from Clemson University, and this is our transtibial ankle prosthetic.
The global health challenge that we aim to solve is the unavailability of affordable assistive prosthetics in developing countries. Currently, available ankle prosthetics don't meet the unique needs of these amputees. Our team aims to specifically focus on rural areas in India where the most common solution for transtibial amputees is to be fitted with a static ankle, meaning a fake foot, such as the sock or Jaipur prosthetic. These aid with shock absorbance but prevent any stimulation of either the ankle or subtarsal movement.
Our solution is to develop a dynamic prosthetic with the responsive nature to mimic normal gait patterns and reduce the risk of further injuries associated with static prosthetics. Our design requirements mandate that the materials chosen must be low cost, readily available, and able to endure heat, dirt, and humidity. The prosthetic needs to be affordable, lightweight, and functional. Working with our contacts at the Indian Institute of Technology in Delhi, we plan to bring our prosthetic to rural communities in India and communicate with local clinicians, where the device will be able to be manufactured locally and easily repairable.
Our design solution is to create an ankle prosthetic that mimics the shape of a foot while incorporating low-cost muscle wire and sensors that respond to changes in terrain, creating a dynamic prosthetic that allows for farmers to return to work and participate in cultural and daily activities pain-free. The structure of the base is designed to maximize shock absorbance while supporting the weight of an adult and will be fitted inside a foot mold to mimic the shape of a foot. The dynamics of the prosthetic are controlled by muscle wire, which is a shape memory alloy, meaning that it reacts with an applied voltage. The muscle wire will be in the shape of a spring and strategically placed along the ball joint of the ankle. As the current runs through the material, it extends and contracts to allow for movement within the ankle. The sensor, which will be placed at the optimal location on the bottom of the foot, will communicate the position of the foot to the muscle wire, which will be programmed to respond accordingly, allowing for the user to successfully complete the gait cycle unperturbed.
We have successfully constructed a 3D model of the prosthetic that is capable of withstanding 9,000 newtons of force and can endure a lifetime of approximately 2 years. Stress-strain testing of the muscle wire has indicated promising use in the design to allow for ankle mobility. The properties of the muscle wire will continue to be evaluated to be effectively programmed to the sensors to communicate with the muscle wire during different phases of the walking cycle. Further steps would also include physical gait analysis studies, testing and implementation of the sensors into the prosthetic sole, and evaluating the optimal material to be used to create the prosthetic.